we're talking equivalence. Before we get started too much, I'd like to make a few observations. Your text talks about two. I think they're worth repeating on equivalence. First is that equivalent cash flows are equivalent at all times. This is important because what it means is that I can compare a cash flow at any time that is convenient to me. If it's convenient to compare the cash flow in its present value, fine. 6 months, fine. 3 years, whatever point in time is convenient, I can compare them. And if they are equivalent, they will be equivalent at all those points in time. If one is higher, it will always be higher. If one is lower, it will always be lower. The exact amounts may change. But generally, in equivalence, I am looking at comparing two machines, two buildings, two manufacturing processes. I want to know which is more expensive and if it's 20 or 30 or 40% more expensive. And this is a very convenient thing for me to know. A second thing to know is if you change the rate between the two cash flows, you destroy equivalence. Now, this is important because you may have machines, for example, where one person is going to give you a lease at 0%, one at 10%. Well, they may have been equivalent before you got the lease factored in, but the change in interest rates will destroy the equivalence. And so equivalence depends very much on having the same rate. And if I have a given rate at a certain point in time, and then I change it for another point in time, that will also destroy the equivalence. So to always be equivalent and to be able to pick my point in time as a result, I have to have the same interest rate. Another one is that you have to convert all cash flows to the single point, to a single point and flow. This kind of seems obvious, but it's amazing how often people will forget it. Maybe I have a cash flow where I got some cash and I got some more and I got a little more and then I paid it. And I said, well, I want to know and I have another cash flow that I'm just making a bunch of payments and then I get some cash out. And I want to compare these to yet another option, but this is one option. Well, some people will forget and they will say, well, this cash flow here, I'm going to project all these numbers to a period in time, and then I'm going to add that to this sum over here. You can't do that. All these individual items need to be projected to this period of time, as do all these items need to be, and then they need to be added together. In other words, every cash flow, if we're talking about a machine that has 6 different pieces to its cash flow, every single piece must be projected ahead appropriately to make a comparison. We can't project some pieces and not others. It destroys the idea of equivalence. Other thing is equivalence is true for all parties. For all parties. So in other words, if I have a lending transaction equivalent, it's equivalent whether I'm loaning the money or borrowing the money. Doesn't matter. One will be plus, cash to me, the other will be minus cash from me. But they will still be equivalent. And in fact, it'll go beyond that. If I'm getting money, if one gives me more money, then the one who borrowed will be getting less money. So it's even more than we both see it. The equivalence, it's also, if it's one's more expensive for me, it'll be, more profitable for me, it'll be more expensive for you. It makes sense, but again, it's one of those things people tend to forget. Now, there are a number of cash flow formulas. The cash flow formulas are basically series formulas from mathematics. You should look at them and have them immediately look familiar. Think, oh yeah, I've seen those some of series formulas before. I've derived them before. And so other than pointing you towards them and pointing out to you, by the way, these are formulas you might want to put on your sheet of notes. They're handy, but you've seen them before. You may not remember them well, but you've seen them before. The basic formulas people use are uniform series, and it's just like it sounds. The cash flow is, well, you have a constant payment. This constant payment, by the way, is called an annuity. So if someone talks about an annuity, they mean they're getting a constant payment for a certain period of time. If you say you annuitize something, it means you have a given amount of cash and you change, you give it away or change or invest it or some way, you make the cash you have right now into a series of payments, constant payments over time. That's annuitization. People would be most familiar with annuities from either savings plans or retirement plans. But that is the meaning of annuity. It's a constant payment over a given time. Of course, with inflation, the value to you is going down over time, but annuity simply means constant payments. Then there is linear gradient. The idea behind a linear gradient is we start off at 0, and then we go up at a constant rate. So there's a constant slope. Maybe every period of time we add a certain amount. We take this old payment plus some new payment. And we keep doing that over a period of time. We can develop a simple formula for that. You should have seen it before. It's a linear gradient. Then we have geometric. Well, it's just like it sounds. We should have seen this before. Geometric, it's simply you start at 0 and it goes up geometrically. So each piece then is going up by some factor. So if we started off with the first piece being something A, then this increase will go up as 1 plus some interest to some power. It's geometric. Now, again, it should be something you've seen before. This, by the way, is uncommon for payments to do this. Usually if they do this, it's because someone's trying to make payments automatically adjust for inflation and they're assuming inflation. But it's not often done. But that is geometric. And then there's mixed, and mixed is just like it sounds. Add 2 or 3 of them together. So, for example, a common thing is we start out, instead of starting out at 0, we start out for a fixed amount, some fixed amount B, and then it goes up in a straight line from there. This is mixed because you can analyze it as a constant payment, an annuity, so this part's an annuity, and this part is a linear piece. And so you can analyze them separately and add them together. That's mixed. And like I said, you find these in your text. They're also given, by the way, at the front of the text as formulas. They're pretty straightforward. Now, the other cash flow that is, of course, which is the first one we looked at, is a single payment. This is the most important because it allows us to do pretty much everything. And with a single payment, remember, we have a present value, we have a future value, and in general, for a compounding relationship, we say that the future value is equal to the present value times 1 plus the interest rate raised to the number of time periods. And that's the general projection for between future and present. And is, again, fundamental. If you don't remember any of the formulas, you can always do a future value by taking each and every piece of a cash flow. Let's say it's annuity. You take each and every piece of the annuity. You project it to wherever your future is supposed to be. So this one would be your annuity payment times 1 plus I, and then Your next piece that you project forward is going to be your annuity payment times 1 plus I squared. And the next one is the annuity payment times 1 plus I cubed. You can always do it by hand and just add them up separately. So if you don't remember the formula, you can always do them this way. If you're familiar with a spreadsheet and you have a spreadsheet, you can always take the spreadsheet and quickly program it out. So this is probably the most fundamental and useful, generally useful relationship, but these others can be handy shortcuts if you remember them. When you're talking about a single payment, by the way, there is a good rule of thumb called the Rule of 72. I've also heard it called the Golden Rule, but it's the Rule of 72. The idea is at a rate I per interval, how many intervals, how long, for something to double. Well, let's just say the future value is 1, or excuse me, the present value is 1, and we want a future value then double that, or 2. So we'd say the future value 2 is equal to the present value 1, I won't write the 1 down, times 1 plus the interest rate to the nth power. And we're trying to solve that. Of course, we don't know the interest or n, we know one of them. We'll know the interest or we'll know n. We don't know them both. Well, let's take the logarithm of both sides. So I have the logarithm of 2, and that's n, times the logarithm of 1 plus I. Let's assume the interest rate is low, like 7%, 2%, 2%, 0.02. We know from an expansion that this is going to be about the interest rate. So the logarithm of 2 is 0.693. The interest rate, this is approximately I, so this is NI, so it's about NI. So you might say, well, gee, that looks like a rule of and by the way, because the interest rate, since I in this formulation is the percentage, means it's less than 1, so I'm going to multiply both sides by 100. That means instead of saying 0.07, I'll say 7%. And so I will just, so I take it by 100, and lo and behold, I get 69.3 equals NI. Wait a minute. Where I is now 1% equals 1. Wait a minute, you said 72. That's 69. Well, the thing is, as I vary, there's a simple observation that if I talk about this value, if I talk about this, the value that works over time for this product of Ni, what you'll find is from roughly about 75 down to about 69, as I vary I, this product kind of does something like this. It's down around 69, it's up around 75, and so right in the middle is about 72. And so a better number for this product turns out to be 72. It's just an observation. Your text goes through interest rates of 5, 10. What does this product actually is? It's about 72. And so the rule is the rule of 72, not the rule of 69. And it's that because over practical ranges of interest, over things we're really interested in, product's about 72. Now, I've used this time and time again. It's very handy. You're in a meeting. Someone says, I want to know, I have an interest rate of, 30%, and it's growing so much. How long before it doubles? Well, or how long before it grows 11%, 10%? Yeah, so here's the way you use it. You say, well, plus 10% is 1.1x. Okay, let's see. What do I know about 1.1? Well, 1.1 squared is 1.21. Not there yet. 1.21 squared, 1.41. Or what? 1.41 squared, it's about 2. It's 2. Okay, so I have 1.1, 2, 4, 6. So I can quickly say 1.1 to the sixth is about 2. If you're not used to doing these sort of mental calculations, I would really suggest you get used to them. They're very valuable, and you can get in meetings, make all sorts of discussions and chats. If you have to keep looking things up and calculating and so forth, you're going to find that decision making and estimating just slows way down. So a lot of these rules of thumbs are things that, as an engineer, are best for you to just have in your mind and get used to. If you're not used to this, to something like this, you should practice a bit. Anyway, so now I know I can look at it and say, oh yeah, 1.1 to the sixth power is 2. So how long does it take to double? Well, let's say I have 8%. If I have 8%, well, then the rule of 72 says 72 divided by 8, 9. It takes 9 years to double. Now this is logarithm, right? Since it's logarithm, a power is just a divisor. So 1.1% is going to take, well, I have 6 times 9. 6 times 9, or 54 years. It takes 54 years. You can do that while just looking at it. If you can't do it while looking at it, well, then some practice will help you do it by looking at it. But it is that sort of calculation. It's I can't tell you how many times I use this rule. I use it many, many times a year, because they'll be talking about a cost or growth of a product line, when's our sale going to double, and so forth. And it's important to be able to look at it and say, well, it's about so long. And that's important decision making. Rule of 72. Well, what about some of the other formulas? Well, one of the important ones is called a sinking fund. Your text talks about that. Sinking fund. This is a special annuity. Remember, annuity, constant payment over time. It's called a sinking fund because the idea is I buy some equipment for $10,000. I'm going to buy another one to replace it. How much do I have to save every month or year? How much do I have to set aside to buy the replacement? And that's a sinking fund. So I have a goal in 5 years to buy something, a car, a machine, whatever, and I set money aside. And that's a sinking fund. Now, this is basically an annuity. And so we're back to the idea it's a constant sum, and that is equal to some large future value. This is my goal, is to achieve that. And so if I look at the annuity formula, it says that the future value is equal to the height of these, the annuity, times 1 plus the interest rate to the number of periods minus 1 divided by the interest rate. Now, actually, I know this. So this is the annuity formula. I know this, or constant payment, whichever you prefer to call it. What I really want to know is what's the payment, and that's what's the sinking fund formula. And it's just turning it around. So what I have to pay every period is just going to be the amount I want to wind up with times the interest rate, or earning rate, 1 plus I to the nth minus 1. So if I have a car that I want to buy in 5 years, and it costs $20,000 now, so I'm guessing it'll cost $25,000. What I do is, that's $25,000. Interest rate, well, maybe I can get 1% on savings. Not much today. But so the interest rate would be 1%. It's compounded monthly usually. So in 5 years, monthly compounding is 60 periods. So I would say the annuity is equal to, well, I said 25,000. 25,000. It's going to be by, I said the interest about 0.01. It's going to be divided by 1 plus 0.01. to the 60th power minus 1. That's how much I have to save every month. So that in 5 years, I have the cash to buy the car. By the way, I suggest any big purchase, you plan ahead and do something like this. It's always cheapest for you as an individual to pay cash. It's always cheaper unless you have a super investment, which maybe you do, but generally you don't. Whereas companies, it's usually cheaper to borrow, not always, but usually, and the borrowing is because of tax benefits, and we'll talk about those. As an individual, you're not getting tax benefits by using your car. As a company, you are. So there makes a change there. I'd also suggest, by the way, every single time I have a new grandkid, I start a new fund for their college education, and I start putting money in according to a sinking fund. I've done that for each of my children over the years, so when they got ready for school, the cash was there. So it's a very handy thing for individuals as well as for a company environment. It's a sinking fund. Now, let's take a look here at the sinking fund formula. Here again is what I just wrote a minute ago. The annuity is the final end result that you want. I divided by 1 plus I to the nth minus 1, and it is written as F times the annuity value divided by FIN. As soon as you see that, you know that's a sinking fund formula. Many of these are directly functionally into Excel or other spreadsheets, like I said. So you should be familiar with a spreadsheet. You can use them on your homework, although I think it's better to do them by hand. You can't bring a spreadsheet into class, but you can bring in a financial calculator you bought, which has this programmed into it. Doesn't matter to me, but here would be the Excel function. It's payment, monthly payment, and it has the factors in it for Excel. Now, here they have an example of 3 different payments. And what they're looking at here, and I wanted to take a quick look at this, is they're looking at here 3 different annuity factors and asking, well, what do we do with them? Well, whenever we get these compound things and we're looking at equivalents on the compound, we simply use the different factors because all these equations are linear. That is, you can directly add them or multiply them. They're not squared laws or square root laws, they're directly linear. So, for example, if we want to compare a cash flow like this is an annuity, right? But when this annuity is done, we're not really going to touch money till over here. So, the way you would calculate this annuity is you would add up this part of the annuity to get a sum here, and then you consider that a single payment, and the second part is you project the payment here to here, and that gives you the correct answer. And so it's a 2-part type investment. Now here's another one that they're comparing in this problem. Again, it's an annuity here, but this annuity doesn't start right away. It doesn't start at time 0. It starts after 10 years, I believe. Yes, 10 years. And then it runs to the very end of time, and you can find out. So this one, what you do is you take and you can do one of 2 things. You can just project this forward, or you can project the sum backwards and then go forward. This one is constant over the entire period of time. Now they're talking about comparing investments, by the way, and so let's just take a quick look. I'll move it over a little bit so you can see. They have plan A, B, and C. And they're showing us what happens if we spread an investment over all of time, just at the start of time, first few years, or just at the last few years. And you can see, well, if we put money in an investment plan right away and then we quit spending, so it just grows over time, they're projecting $315,000. If we wait and don't do anything and then we put money in later on, they're projecting $250,000. And if we put a continuous stream of money in, we get $560,000. All 3 of these we put in the same amount of money. In other words, in the problem, I'll let you look at it because I'll post this. as you look at it, if you add these up, or add these up, or add these up, you put in about the same money. But you get dramatically more result because this is compounded longer. It's compounded longer because we're taking the future, 8%, 31 years. Big factor. And so this is what's making this bigger than this. Because in this case, we're only starting here. We're not starting way over there, and so we've missed all this compounding. And of course, if we keep compounding all along, it does the best of all. And so it's just an example of where you use two pieces. You either add them or multiply them depending upon what you're doing. We can do an addition to here, and then we can project the number to there and compare it to other numbers because we projected with the same interest to the same point in time. And so our numbers are directly comparable in this case. That is what we said earlier, and that's correct. Well, let's see. Okay, here is a uniform series again. In this case, and this is what we've done here, is we spent $250,000, and then we have to spread the payments off to pay that out over time. This is like a sinking fund. It's a capital recovery factor. The only idea here is instead of going to a future value, where we're saving money to buy something, we've already bought it, and now we're trying to pay back what we bought. It's the only difference. So one is the future, one's the past. If we've already bought it, well, then it's capital recovery because we're getting back our money. If we haven't bought it yet, it's sinking because we're getting ready to buy it. That's all the difference is. Same formula, basic same formula, you notice, although here we've cast it in terms of the present value. And again, you can look this is the annuity equation. It's just done in a certain format. And it's very important because we often talk about capital recovery, or we often talk about establishing a sinking fund for things. Again, I will post this, but you can see the examples in your text. I just wanted to make sure I pointed that out to you clearly. I'm going to put that away. I'm going to put this away for the moment. Because the one other thing I wanted to make sure I spent a few minutes on, and we're not done with this chapter, although we're going to move on a bit, is you should, again, be familiar with the spreadsheet. I have to admit, I tend to use a different version than the current versions of Excel, and they keep changing things and rearranging terms. They all do the same thing over time. They just get a little more functionality or graphing or whatever. So you should be generally familiar. Use them every now and then, or use them often. You can solve all sorts of problems. Financials are particularly good, but you can solve motion problems, and you can solve resistance and distributed resistance and all sorts of problems with a spreadsheet. What I was going to do was just show you quickly that the financial functions are in here in this type of format we've been looking at. So I'm going to take a square and put an equal sign so I can get to the functions. Here are the functions in Excel. Hit the button. If you're not familiar, there's all different forms of functions you can get, engineering, text, and so forth. We want financial, so I'm going to go to financial, and we'll be talking more and more about these different terms, but right now what we're really interested in is future value. Future value, is what they have. By the way, you notice Excel's using a different nomenclature than our text, right? It's not F, it's FV. And then it's slightly different format on the terms. But let's take a look at it. So if I say it equals future value, let's pop it in. Wants to know the rate, whatever my rate is, I don't know, 0.07%. Wants to know how many periods, 10 periods. And they want to know what the payment is. And I'm making a payment constantly over 10 periods, so let's just say it's $1, and it'll tell me. Okay, so if I paid in $1 every period for 10 periods, that's $10 paid in, and I got 7% interest, then the value, when I got all done, the future value, is going to be, what, $13.8. That's what it tells you. Okay. Now it came out a negative number because I was saying I was paying in and it belonged to me. This negative number is, it assumes that these are payments that are paying off a debt, and so they're telling me what the negative sum is, the negative equivalent is, not that I'm paying into a fund for myself, so it's negative. So you have to remember which way the equation's working, but it's very handy. Let's just look at another one. Let's say equal, and let's find, how about finding payment. Okay, payment. The payment for a loan based on constant payments and a constant interest rate. That's the same as an annuity, right? It says, and actually it's the same as this, as a recovery. I tell you how much I spent, 100,000. It's like I borrowed it. I tell you the interest and how long I'm going to pay it off. It tells you how much to pay. So let's just stick that in there. The rate, I don't know, let's take 10%. Number of payments, I said 5 years, 60. And what is the present value that I want it to be? I want to get 150,000 or dollars or whatever. I've got to pay 15, roughly 15, each period for 60 periods. You notice, by the way, 15 times 60, I'm going to pay out 90, 900, and yet I'm only going to get 150. Well, that's capital recovery under interest rates. So we're not going to do a lot with Excel. Every now and then I'll show you something in Excel. There's other spreadsheets. I happen to like Apple's spreadsheet much better. Apple works much better, but there's Google spreadsheets, and there are all sorts of them. They work all a little bit different. So it's good to have a spreadsheet you're relatively familiar with. You're not going to be allowed to use them on quizzes, but most of the problems are going to be simple enough. It shouldn't be an onerous calculations as long as you understand how to do them. Well, we'll talk a little more about this chapter, and like I said, I'm going to be posting the PowerPoints from the text online. Make sure you read the text. Pay attention to these formulas. They're easy things you may use later on. You don't really have to know the gradient formula or the annuity formula, because you can project each element individually and add them. That works just fine. It's just a little longer. So for now, I guess I'll say goodbye.